All right, welcome everyone. We have actually reached the end of the semester. So today will be the last lecture. And I suggest that instead of taking a 15-minute break after the first lecture, we'll keep going for 10 more minutes or so, and then we'll end it. So I'll try to finish within 1 hour. Just a couple of pieces of practical information to begin with. The exam date for this course has been set now, I believe, June 1st. And information about the wheres and whens will appear, I think, 3 days before the actual exam. So you have to keep an eye out for that. Now, before the exam, it's customary to have some sort of question hour where you can sort of pose all the things that you wonder or all the questions you have before the exam. So my suggestion for a date would be the 25th of June. That's a Friday. And at the same time as the exercise guidance hour is usually conducted. Yes?
We have optics exam.
Oh, okay, you have that. How about the 24th? Is it better? Okay. So let's aim for that. So I'm not sure about which room is available then. But we'll find a room. Okay, so let's take 24th. And same time as the lecture is usually, so oh, sorry, it's okay, so let's do 10 instead of 8. Yeah.
Isn't a good idea to have it before?
Oh, I'm sorry. That's a good idea. Let's make this May. So I suggest 10 o'clock instead of 8 o'clock. And we can meet at the exercise guidance room. So it's possible we might have to change room, but we'll meet there in any case. Yes. I think that's it regarding practical stuff. Do you have any questions about practical issues related to the exam or this course? You will also have the opportunity to ask during the question hour, of course. All right, so the plan for today is to finish this example that we commenced the last time, the harmonic oscillator treated with Hamilton-Jacobi theory. And after completing that, I will try to give a summary of the entire content of this course and try to draw some sort of connections between the different topics that we've studied for you to get an idea of the entire picture, so to say. Oh, by the way, one final thing. We'll have a reference group meeting actually after this hour, this lecture. So it's your final opportunity to give any feedback you would like to sort of express concerning this course, the lectures, the exercises, anything, any aspect of this course in principle. So if you could all remain for 5 or 10 minutes to just give your feedback to the reference group, that would be great. Okay, Hamilton-Jacobi theory applied to the harmonic oscillator. And just to recap sort of the virtue of the Hamilton-Jacobi theory, its main strength, I would say, is its capability to treat time-dependent Hamiltonians. So the trick we used, or the main idea is to take the Hamiltonian, the original Hamiltonian describing your system, and then performing a canonical transformation on the coordinates and the canonical momentum, so that the new Hamiltonian is 0. And we can accomplish this by means of the generating function, and in particular the generating function of the second class, as we had a look at. Because if we obtain a Hamiltonian in these new canonical coordinates, which is 0, then we are guaranteed that these new canonical coordinates will be conserved because their time derivatives will be 0. So we had applied this to the standard form for the harmonic oscillator Hamiltonian, and we had identified Hamilton's principal function. In the following way. Now, with this function in hand, we have essentially all the information we need to solve the problem. And again, let me emphasize that when I say by solve, but what I mean when I say solving the problem is to identify the time dependence of the generalized coordinates and the canonical momenta. Because if we know the time dependence of those quantities, then we know exactly how the system evolves with time. So I believe where we ended last time was that we had identified the time dependence of the spatial coordinates in the system. With the following quantities. So omega here is just the frequency dictated by the spring constant and the mass of the particle. Alpha we had identified as the energy due to the fact that the Hamiltonian in this case was time independent. So energy has to be conserved. So we have basically half the solution here. Now we have to identify the time dependence of the momentum. And to do this, we just follow our recipe. I believe we listed a 4-step sort of strategy for solving a problem with the Hamilton-Jacobi theory. And the next step is to identify the momentum, having now obtained Hamilton's principal function S, simply by partially deriving it with respect to Q. Which gives us this. The derivative with respect to Q, when we have an integral like this, is by the fundamental theorem of calculus, simply given by the integrand. So we can now take our solution for Q and insert it into here. Which gives us sorry, I don't think it should be a square here. Yeah, that was a typo. Okay, so we have 2 alpha over k and then q squared, and this is q, so we get 2 alpha k. Should look something like this. Well, we can make a simplification here because we have the same prefactor. So this is just cosine. So the final result is this. And so by now we have identified the time dependence of q, the spatial coordinate, and the canonical momentum, and so we have solved the problem. So the main ingredient in this method is to identify Hamilton's principal function. And this is sort of a trivial example because it doesn't really show the full potential of Hamilton-Jacobi theory, since this Hamiltonian is time independent, for instance. But it's just to show sort of the order of the steps. Okay, so we've obtained a result. Let's take a look and see if this is reasonable. Okay, so this varies as a sinusoidal function plus eventually, or possibly some phase shifts. Now, can we say something more quantitatively about whether or not these expressions for Q and P are actually correct? Or put differently, do we know of any relation that P and Q should satisfy in relation to each other?
And combining the Hamiltonian should give a constant energy.
Mm-hmm. That's true. So inserting P squared and Q squared here, we should get a constant energy. Absolutely. Now there's one more relation. So let me just write this. So the first, precisely as you point out, just plug it into the H and check if it's a constant. But we also have this, just the very definition of momentum. So we can just check briefly if this is the case. Well, we derive this with respect to t, so we get cosine, that looks good. But then we also get an additional factor, omega. And omega being defined like this means that the k's should cancel and we get an extra m. So it looks correct. So what I would like to do now is to attempt to give a complete summary of this course in the way that I draw sort of a diagram which connects different topics in what is hopefully a logical and intuitive way for you. So the purpose of this is that I would like to not only emphasize the most important sort of points that we raised for each topic in this course, but also so that you can see how these are related, hopefully. When I did this last year, I had two blackboards. I had one blackboard I could just raise up and down, I think in R8. I don't have that here. So the problem is that this board is not sufficiently large for the entire diagram. So what I'll do is that I'll draw the lower part of this diagram, just so you know that there will be something above, and then I will take that part. So what I give now is just the lower part of the diagram. So let's see if we can make this work. So as you know, the two most fundamental concepts in this course have been the treatment of Lagrangian and Hamiltonian formalism. Now, these formalisms have some features which are common to them. For one thing, we need a description of the system. So we need a set of what is known as generalized coordinates. And in the Hamiltonian formalism, we also need these canonical momenta, which may be obtained in this Lagrangian formalism as well. Let me write it like this instead. Now, the way that we move between the Lagrangian and the Hamiltonian formalism is by means of the Legendre transformation. Where essentially the Lagrangian is obtained by subtracting from the Hamiltonian a product between the two variables we want to interchange or exchange. And another common feature of these two formalisms is that we're ultimately interested in some equations of motion in order to identify the time dependence of the quantities that we want. So we have the Lagrange equations on the one side and we have the Hamilton equations on the other side. Now the way we obtain these equations of motions formally, the manner in which we derive them, is by using either D'Alembert's principle, in this case, or Hamilton's principle. So there are several ways we can derive the same physical content contained within the equations of motion. And the final point here well, what would you list as the third point in terms of an important aspect which is common both for Lagrangian and Hamiltonian formalism?
Conservation laws?
Yes, conservation laws and symmetries. So the idea here is that if the Lagrangian or Hamiltonian have some sort of symmetry, well then there should also be something that is conserved. We've had a look at how translational symmetry corresponds to a conservation momentum, rotational symmetry corresponds to angular momentum conservation, and time independence of the Hamiltonian, or time invariance, dictates that we have conserved energy. And let me also mention a couple of concepts which are important related to this. We've said, we've talked quite a lot about cyclic coordinates, which is related to the symmetry of the Lagrangian, for instance. So if we have a cyclic coordinate, then the corresponding canonical momentum is conserved. And we also discussed Poisson brackets in terms of making a statement about whether or not a physical quantity f is conserved. Okay, so this is sort of the framework, the skeleton of both of these formalisms. And we've had a look at a number of applications. So one application we had a look at was central forces. Now, central forces depend only on the distance from the force center and have no angular dependence, meaning that we have a rotational symmetry. Now, to characterize various situations where particles or objects are scattered by such central forces, or influenced, if you will, by them, we have discussed the concept of a scattering cross-section, which basically quantifies both the range and the magnitude of a force, whether it is repulsive or attractive. So the scattering cross-section can be used to characterize both situations. And we were mainly concerned with a Kepler potential when discussing these central forces. And we discussed in detail how you could obtain various quite different particle orbits depending on the parameters in the system. And we saw that although we started out with a number of parameters, the magnitude of the potential k, the mass of the particle, the angular momentum of the particle, etc., all of these could be reduced to an effective dependence on a small number of parameters, namely the energy and the orbit parameter, which we introduced. So we saw that depending on the energy of the particle moving in such a Kepler potential, we could obtain various types of orbits. Bound states or non-bound states, to be more specific. So that's one application. Another application where we used this framework was in the context of small-scale oscillations. So what we discussed here was a situation where we considered a small perturbation on a system from its equilibrium point. This equilibrium point could be either stable or unstable. But in the case of a stable equilibrium, we saw that this perturbation would give rise to an oscillation, effective oscillation around this equilibrium point. And we derived a formalism formalism for how we could treat basically coupled oscillations in such a system. And two important concepts here were eigenfrequencies and eigenmodes. So we saw that the general solution for this type of system would consist of a linear superposition of these eigenmodes with belonging eigenfrequencies. One of the main results when we treated this topic here was that we could simplify the problem considerably if we were able to obtain the normal coordinates of the system. Because in the normal coordinates description, we would have a set of uncoupled harmonic oscillator equations of motion. So one should always try to find the normal coordinates of this system where you have coupled oscillations. So let me try to write the third one here. Namely, rigid body dynamics. We consider the rotational motion of rigid bodies. Well, since the bodies are rigid, we don't need to take into account any possible deformation or radial dependence of the points in the body, because they would all be fixed relative to each other, which means that we could use the so-called Euler angles as our generalized coordinates. And when deriving both the equations of motion and various physical quantities such as angular momentum and kinetic energy for such rigid bodies rotating, we saw that the moment of inertia basically played the role of mass in the system, but it would take into account both the mass distribution of the object and its shape. And the final aspect that I would like to highlight regarding rigid body dynamics was that we considered fictitious forces, namely that the time change of vectors would be perceived differently in two coordinate systems where one would be rotating relative to the other. As an example of this, we considered the Coriolis force. And this is related to the fact that not only does the vector change, but also the axis describing the system change with time. So that's why you get an extra term in the time dependence of the vector. So I would say that these are probably the main applications that we've used this framework for, and this is the general structure of the formalism that we've applied. So let me then move on to the upper part of the diagram. So we have Hamilton formalism down here. And there are a couple of features that pertain specifically to the Hamiltonian formalism that we've highlighted towards the end of the course. We've discussed the concept of canonical transformations, where we essentially transform both the spatial coordinate and the momentum into a new set of coordinates in such a way that this transformation is canonical. And what I mean by this is that the new coordinates in the system also obey Hamilton's equations for the new Hamiltonian. So it's not just any transformation, but it's done in a specific way which guarantees that the new Q and the new P also satisfy Hamilton's equations. And we saw how this could be used both to simplify a Hamiltonian in order to make a coordinate cyclic, which is always good, but it could also be used to sort of rewrite a Hamiltonian which looked alien and strange to begin with into a more familiar form. Now, a tool that we used in order to guarantee that a transformation will be canonical when moving between an old set of coordinates small q and small p to a new set large Q and large p was the generating function. So we introduced basically 4 classes of these generating functions, and the common feature for all of them would be that they depended on one of the old and one of the new variables. And as an application of this, we have discussed Hamilton-Jacobi theory, where we utilize the generating function of the second class in order to make the new Hamiltonian 0. Since we always have a freedom between, we have a relation between the old and new Hamiltonian where the difference can be given as a time derivative of a function. So we use this freedom in order to make it 0. And this gives us the opportunity to treat time-dependent Hamiltonians more conveniently, for instance. So these features pertain specifically to the Hamiltonian formalism. Now, all of the diagram below here that we drew initially, can be considered either relativistically or non-relativistically. So you can basically think of that as sort of an overarching classification. All of the stuff that we wrote here can be considered either relativistically or non-relativistically. So key concepts regarding this topic was, for instance, the Lorentz transformation. Which we used in order to move between different inertial systems. In effect, coordinate systems that moved with a constant relative speed to each other. And we didn't say very much about the general theory of relativity, but we considered the special theory of relativity quite a bit. And in particular, this special theory sort of rests on 2 fundamental postulates about the constant nature of the speed of light and also the equivalence of physics in all inertial frames. So we basically made this first postulate a bit more quantitative by discussing covariant physics in different inertial frames. That the laws of physics or equations of motions should basically have the same form in all inertial frames, so that we would have the same type of physics, regardless of which coordinate system we were located in. Let me just remind you also that there are unfortunately two sort of uses for the term covariance. One term relates to this invariance of physics, the other is related to covariant and contravariant vectors, which have nothing to do with this. So this is a bit unfortunate, but you need to be aware of it. And on a more technical note, we introduced these 4 vectors in Minkowski space, where you had the 3 first coordinates say something about the spatial position of the object, and the 4th coordinates being imaginary time. So basically, to obtain this constant speed of light, we would have to treat both spatial dimensions and the time dimension on equal footing, so that both of them would transform when moving from one reference system to another. And we also use this invariance of norms to compute various quantities when discussing, for instance, particle collisions. So an important example related to this point was the invariance of the form momentum, which can be used to identify the mass increase in a particle collision, and also the conservation of 4 vector momentum, which corresponds to the conservation of 3 momentum and energy combined due to this 4-dimensional nature. So I believe this should more or less summarize at least the main aspects of this course. And of course there are many details here and subsections that I haven't mentioned. That doesn't mean they're not relevant for the exam, but I would say that these are the main sort of pillars that this course rests on. Is there anything you would like to add or comment concerning this summary? Okay. Well, then this course is actually finished. So we'll have the final reference group meeting now. And in particular, I forgot to mention that you could, one thing you could evaluate is whether or not the changes you requested last time, if you feel that they have actually been implemented. So this is also useful feedback to me, yeah.
Is it worth mentioning gauge invariance of Lagrangians?
Yeah, that's definitely an important issue as well. I didn't mention it here. Yeah, I could have mentioned that as well. That's an important point, that we have this freedom in choosing the gauge of these fields, the vector potential field and the scalar field that define the electric and magnetic fields. So we could choose them to some degree quite freely, still obtain the same physics. Okay, so I would like to just thank you all for this, for attending this course, and it's been a pleasure to give these lectures to you. I feel that you've been a quite active class. You participate in discussions, and we've had conversations along the way. So that's been, I've appreciated that. And I wish you all the best in your exam. So, but I'll see you also in the question hour.